Ladies and gentlemen, today, I am excited to delve into the fascinating world of engineering, specifically the principles behind how boats work. Boats, in their various forms, have been a crucial part of human civilization for millennia, serving as vessels of transportation, exploration, and leisure. Understanding the science behind their operation can enhance our appreciation of these remarkable machines. Boats, as diverse as they may appear on the water, all operate based on fundamental principles rooted in physics and engineering. At the core of their functionality is the principle of buoyancy. When a boat is placed in water, it displaces a volume of that water equal to its own weight. This displacement generates an upward buoyant force, which opposes the force of gravity pulling the boat down. The boat will float as long as this buoyant force is equal to or greater than the weight of the boat. This concept, often attributed to Archimedes, is pivotal to a boat's ability to remain afloat, regardless of its size or shape. Hull design is another key factor in how boats work. The shape of a boat's hull is carefully engineered to optimize buoyancy and reduce resistance as it moves through the water. Hulls can vary significantly, from the sleek, slender hulls of racing sailboats designed for speed to the broader, more stable hulls of recreational vessels aimed at providing comfort and stability. Each design serves a specific purpose, and hydrodynamics plays a critical role in their construction. The streamlined shape of racing boats reduces drag, allowing them to glide swiftly through the water. In contrast, broader hulls provide stability and space for passengers, making them ideal for leisurely cruises. Once a boat is afloat, it needs a means of propulsion to move through the water. Boats can be powered by various methods, such as oars, sails, or engines. Each of these methods relies on the principles of physics to generate forward motion. Oars, for example, rely on the transfer of human effort into energy, as rowers push against the water to move the boat forward. Sails utilize the power of the wind to generate thrust, with the boat moving in the direction the sails catch the wind. Engines, on the other hand, employ various mechanisms based on the fundamental principle of action and reaction, as defined by Newton's third law of motion. Whether driven by human effort, wind, or engines, the propulsion of boats demonstrates the application of engineering principles in achieving the desired movement. Stability is a critical aspect of boats' design and operation. Engineers carefully consider how to balance a boat to prevent capsizing. This balance is achieved through the placement of weight and ballast. In the case of sailboats, the keel, a heavy fin or bulb-shaped structure beneath the boat, serves as a counterbalance to the force of the wind in the sails. It prevents the boat from leaning excessively and helps maintain equilibrium. Stability design is essential not only for safety but also for ensuring the comfort of passengers and crew during the voyage. Control and navigation are achieved through various mechanisms on a boat. Rudders and other control surfaces are engineered to change the boat's direction. These control mechanisms are designed based on principles of fluid dynamics and hydrodynamics. The shape and position of the rudder determine how water flows around it, allowing the boat to turn in the desired direction. Additionally, navigation systems, often employing principles of GPS and celestial navigation, play a vital role in ensuring that boats reach their intended destinations safely and efficiently. Safety is a paramount concern in boat engineering. Design and technology are used to develop life-saving equipment, communication systems, and navigational aids that protect both passengers and crew during their journeys. Modern boats are equipped with various safety features, from life jackets and lifeboats to advanced radar and communication systems, to ensure the well-being of those on board. Boats are remarkable feats of engineering, blending principles of physics, mathematics, and design to navigate the world's waterways. Understanding the principles of buoyancy, propulsion, stability, and control allows us to appreciate the science behind these vessels that have shaped human history and continue to serve a myriad of purposes today. The next time you set sail or admire a boat in a harbor, Take a moment to marvel at the intricate engineering that enables these vessels to gracefully glide across the water. At the heart of a boat's functionality lie the fundamental principles of buoyancy, propulsion, and stability. These key principles are the building blocks that enable boats to not only stay afloat but also to navigate and serve various purposes, whether for transportation, recreation, or exploration. Understanding these principles is essential in appreciating the intricate engineering behind every vessel. Buoyancy is the foundational principle that dictates whether a boat will float or sink. This concept is rooted in Archimedes' principle, which states that when an object is submerged in a fluid, it experiences an upward buoyant force equal to the weight of the fluid it displaces. In the case of boats, the fluid is water. The key to a boat's buoyancy is that the weight of the boat, including its passengers and cargo, must be balanced by the buoyant force exerted by the water it displaces. If the buoyant force exceeds the weight of the boat will float. Conversely, if the weight of the boat is greater than the buoyant force, the boat will sink. The design of a boat's hull plays a critical role in buoyancy. Different types of boats have varying hull shapes optimized for specific purposes. For instance, a racing sailboat typically has a slender hull designed to reduce resistance and enhance speed, while a fishing trawler may have a broader, more stable hull to facilitate the storage of heavy catches. Engineers carefully consider these factors when designing a boat's hull to ensure optimal buoyancy and stability. Once a boat is afloat, it requires a means of propulsion to move through the water. The principles of physics govern how boats move. There are various methods of propulsion, including oars, sails, and engines, each of which relies on different physical principles. Oars, for example, depend on the transfer of energy through rowing, while sails harness the power of the wind, utilizing the principle of lift generated by the curved shape of the sails. Engines, on the other hand, use a variety of mechanisms, often based on Newton's third law, which states that for every action, there is an equal and opposite reaction. The engine expels water or air backward, generating forward motion for the boat. Engineers carefully choose the method of propulsion based on the boat's intended purpose, efficiency, and environmental factors. Propulsion is not solely about movement but also about ensuring that the boat moves efficiently, saving energy and reducing resistance. Stability is a crucial aspect of boat design and operation. A stable boat is less likely to capsize, providing safety for passengers and crew. Stability is achieved through a combination of factors, including the placement of weight and ballast, as well as the boat's shape. Sailboats often employ a keel, which is a heavy fin or bulb-shaped structure beneath the boat. The keel serves as a counterbalance to the force of the wind acting on the sails, helping to maintain equilibrium. Additionally, the boat's shape, particularly the hull, contributes to stability. Wider hulls tend to offer greater stability, while narrower hulls may trade some stability for speed. In essence, understanding the principles of buoyancy, propulsion, and stability is essential for both boat designers and operators. The interaction of these principles guides the design of boats tailored to specific purposes, ensuring they float, move efficiently, and remain stable during their journey. Whether you're an enthusiast, engineer, or someone who simply enjoys a day on the water, recognizing the intricate science behind boat operation adds a deeper layer of appreciation for these marvelous vessels that have been an integral part of human history and continue to shape our world today. The fundamental principle that underlies the ability of boats to stay afloat is Archimedes' principle. This age-old concept, attributed to the Greek mathematician and physicist Archimedes, serves as the cornerstone of buoyancy and explains why objects, including boats, float in a fluid, such as water. Archimedes' principle is essential to understanding the science of hydrodynamics and, in particular, how boats can defy gravity and remain afloat. In essence, Archimedes' principle states that when an object is either wholly or partially immersed in a fluid, it experiences an upward buoyant force that is equal to the weight of the fluid it displaces. To comprehend this principle more intuitively, one can think of it in terms of water displacement. When a boat is placed in water, it pushes aside, or displaces, a certain volume of water. The weight of this displaced water must be equal to or greater than the weight of the boat itself for the boat to stay afloat. This principle is a testament to the delicate balance of forces that govern the behavior of objects and fluids. The downward force of gravity, which acts on the boat's mass, tends to pull it toward the Earth's center, trying to submerge it in the water. However, the upward buoyant force, a direct result of Archimedes' principle, counteracts this gravitational force. When these two forces are in equilibrium, the boat neither rises nor sinks but instead floats at the water's surface. Archimedes' principle has profound implications not only for boat design but for a wide range of applications in science and engineering. It plays a pivotal role in the fields of naval architecture, hydrodynamics, and ship design, guiding engineers in the creation of vessels that are optimally balanced and suited for their intended purposes. Archimedes' principle provides a profound understanding of how boats, and indeed all floating objects, can defy gravity and stay afloat. It underscores the significance of water displacement and the delicate interplay of forces involved in keeping boats buoyant on the water's surface. This ancient principle, still relevant and influential today, is a testament to the enduring power of scientific insights from antiquity and their impact on modern engineering and technology. The shape of a boat's hull is a critical aspect of its design, meticulously engineered to optimize buoyancy and minimize resistance in the water. This fundamental feature is essential for a boat's performance and its ability to navigate through different water conditions effectively. Hull design plays a pivotal role in various types of boats, ranging from racing sailboats to recreational vessels, and its significance cannot be overstated. For racing sailboats, where speed and agility are paramount, the hull design typically leans towards a slender, streamlined shape. These boats are built to slice through the water with minimal resistance, allowing them to achieve remarkable speeds. The narrow hull reduces the surface area in contact with the water, thus reducing friction and drag. Such hulls are carefully crafted to maximize lift while minimizing any tendencies to pitch or roll, ensuring a stable and speedy ride. On the other hand, recreational vessels often require more stability and space for passengers and cargo. Hence, their hulls are designed to prioritize stability and comfort. These hulls are typically broader and more stable, providing ample space for onboard activities and ensuring a smoother ride. The stability of these boats is critical, especially when used for leisurely cruises or activities like fishing and water sports. The broader hull shape increases buoyancy, offering greater stability while also reducing the risk of capsizing. In essence, the design of a boat's hull is a balancing act between optimizing buoyancy and minimizing water resistance, tailored to the specific purposes and priorities of the vessel. The goal is to ensure that the boat remains afloat, even in challenging conditions, and can move efficiently through the water, whether the objective is speed, stability, or comfort. Engineers and naval architects invest considerable time and expertise in studying hydrodynamics and fluid flow to refine the hull design. They use computational tools and conduct extensive tests in water tanks to fine-tune the hull shape, accounting for factors like water turbulence, wave patterns, and wind resistance. These scientific approaches, coupled with years of practical experience, enable them to create hulls that are optimized for the boat's intended use. In summary, the shape of a boat's hull is a critical element in naval architecture. It is carefully designed to achieve a delicate balance between buoyancy and hydrodynamic efficiency, ensuring that the boat remains afloat and can move through the water with the desired characteristics. The variance in hull designs, whether for racing sailboats or recreational vessels, reflects the specific requirements of each boat's intended purpose and the priorities of speed, stability, or comfort. The intricate engineering and careful consideration that go into crafting these hulls are essential in defining the boat's performance and functionality on the water. Once a boat is afloat, it needs a means of propulsion. Boats can be powered by a variety of methods, such as oars, sails, or engines. Each method relies on the principles of physics to generate forward motion. Oars rely on human effort and the transfer of energy through rowing. Sails harness the power of the wind, and engines use various mechanisms to propel the boat forward, such as the principle of action and reaction. Newton's third law, propulsion, is a fundamental aspect of how boats operate, and it's a testament to the ingenious engineering solutions that humans have developed to traverse water efficiently. Once a boat is afloat, it requires a reliable method to generate forward motion, and there are various means to achieve this. One of the most ancient and straightforward methods of boat propulsion is rowing with oars. This technique relies on human effort to provide the necessary energy for the boat to move through the water. As the rower pushes against the water with an oar, they apply force that creates a reaction force pushing the boat forward. This process is governed by Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. In the case of rowing, the action is the rower pushing the water backward with the oar, and the reaction is the boat moving forward. Rowing requires coordination and skill to maximize efficiency and ensure that the boat moves smoothly through the water. It's an ancient and reliable method, often still used in traditional and recreational boating. Sails, on the other hand, are a more passive form of propulsion that harnesses the power of the wind. Sailing is a remarkable demonstration of utilizing the principles of aerodynamics to move a vessel. When the wind flows over the curved surface of a sail, it creates a pressure differential, with lower pressure on one side and higher pressure on the other. This pressure difference generates lift, which propels the boat forward. Sails can be adjusted to catch the wind at different angles, allowing sailors to navigate effectively even when the wind is coming from different directions. Sailing is not only an efficient mode of propulsion but also an art and skill that has been refined over centuries. Engines, whether internal combustion or electric, represent the most modern and powerful form of boat propulsion. These engines rely on the principle of action and reaction, as articulated in Newton's third law. In an internal combustion engine, fuel is burned to create high-pressure gas, which is expelled forcefully from the engine's exhaust. The reaction to this expulsion is the forward movement of the boat. In electric boats, electricity is used to power an electric motor that drives a propeller, generating forward thrust. These methods offer great speed and control, making them ideal for everything from recreational speedboats to massive cargo ships. Boat propulsion is a fascinating area of study and engineering. It showcases the application of fundamental physical principles to achieve the movement of vessels on water, from the simplicity of rowing with oars to the art of harnessing the wind with sails and the power of engines. Each method of propulsion has its own advantages and nuances. These techniques have evolved over centuries and continue to be refined, contributing to the diversity and efficiency of boats used for transportation, leisure, and commerce. Understanding the principles behind boat propulsion allows us to appreciate the intricacies of these incredible machines and the human ingenuity that drives their development. Boats are designed for stability to prevent capsizing. This crucial aspect of boat engineering is fundamental to ensuring safety and functionality on the water. Achieving stability is a delicate balance that hinges on several key factors, such as the placement of weight, the inclusion of ballast, and the boat's specific shape. This equilibrium is especially important for sailboats, where the wind's force can be a formidable challenge. In the realm of naval architecture, achieving stability in boat design is a multifaceted endeavor. The placement of weight, including passengers, cargo, and equipment, plays a vital role. The distribution of this weight must be meticulously calculated to prevent the boat from listing excessively to one side. Even a small shift in weight can have a significant impact on the boat's stability, potentially leading to unwanted tilting and, in extreme cases, capsizing. One of the most notable elements in the quest for stability is the addition of ballast. Ballast is a counterweight intentionally placed in the hull of a boat to lower its center of gravity. By lowering the center of gravity, the boat becomes less prone to tipping or capsizing, making it safer and more seaworthy. The type and amount of ballast used depend on the specific design of the boat and its intended use. For sailboats, where the dynamics of wind and sail can be unpredictable, ballast is often vital for maintaining stability. Sailboats, in particular, face the unique challenge of wind-driven propulsion. The force of the wind in the sails can exert significant pressure, and without an effective counterbalance, a sailboat may tip or even capsize. To mitigate this risk, sailboats are equipped with a keel, which is a heavy fin or bulb-shaped structure located beneath the boat's hull. The keel's purpose is to act as a counterbalance to the force of the wind in the sails. By extending below the water's surface, the keel shifts the boat's center of gravity downwards and outwards, enhancing stability. The design of the keel is a sophisticated aspect of naval architecture, and it is tailored to the boat's specific purpose and the conditions it will encounter. For racing sailboats, keels may be designed to be more streamlined, while cruising sailboats often have heavier keels that provide greater stability but can reduce overall speed. The keel's effectiveness in counteracting the wind force in the sails ensures that the sailboat maintains its equilibrium, allowing for smooth and controlled navigation. Stability in boat design is a pivotal consideration in naval architecture. Whether for sailboats or other watercraft, achieving the right balance through weight distribution, ballast, and the design of counterbalancing structures like keels is essential for ensuring safety, comfort, and performance on the water. Boats designed with stability in mind are better equipped to handle the unpredictable forces of wind and water, providing both novice and experienced sailors with peace of mind as they venture into the world's waterways. Boats are equipped with rudders and other control mechanisms to change direction. The principles of fluid dynamics and hydrodynamics come into play here. The shape and position of the rudder determine how water flows around it, allowing the boat to turn. Boats are marvels of engineering that rely on a variety of mechanisms to navigate the water with precision and control. Among these mechanisms, rudders play a critical role in altering a boat's direction. The principles governing the operation of rudders are rooted in the intricate fields of fluid dynamics and hydrodynamics, which encompass the study of how fluids, like water, behave and interact with solid objects. The rudder is typically a flat, vertical surface mounted at the stern, back, of the boat. Its shape and positioning are carefully designed to facilitate steering. When the boat's operator or captain turns the steering wheel or tiller, it adjusts the rudder's angle in the water. This, in turn, influences how water flows around the rudder. The impact of these actions is what allows the boat to change its course. In essence, the rudder exerts control over the boat's heading by manipulating the flow of water. As water rushes past the rudder, it creates a pressure difference on either side of the rudder's surface. This pressure difference generates a force known as hydrodynamic lift, which then initiates a turning motion. The science behind this phenomenon is deeply rooted in Bernoulli's principle, which states that as the speed of a fluid, in this case, water, increases, its pressure decreases. When the boat's operator turns the rudder, it alters the water's flow pattern around the rudder, and, as a result, the pressure on one side becomes lower than on the other. This pressure differential pushes the stern of the boat in one direction, which, in turn, causes the boat to change its course. The effectiveness of the rudder's action depends on several factors, including its size, shape, and the boat's speed. Larger rudders and boats moving at slower speeds may require more effort to change direction. Additionally, the interaction between the rudder and other hydrodynamic elements of the boat, such as the keel, can also influence the boat's handling and turning capabilities. Understanding the principles of fluid dynamics and hydrodynamics as they pertain to rudders is essential for anyone involved in boating. From experienced sailors to naval engineers, it underscores the importance of rudder design and placement to optimize a boat's maneuverability and responsiveness to the helm. Moreover, it highlights the incredible harmony between engineering and the natural world that allows us to control these magnificent vessels as they glide across the water. Engineering also plays a critical role in ensuring the safety of boats. This is a paramount concern in the world of maritime engineering, as the well-being of passengers and crew is of the highest importance during any journey. The responsibility to design, implement, and maintain safety measures falls squarely on the shoulders of marine engineers. One of the primary aspects of boat safety is the design of life-saving equipment. This encompasses the creation and placement of life jackets, lifeboats, life rafts, and other critical safety gear. Each of these items must be engineered to withstand the harsh marine environment, including exposure to salt water and extreme weather conditions. Life jackets, for instance, must not only provide buoyancy but also allow freedom of movement for passengers and crew in the event of an emergency. Furthermore, the design and placement of lifeboats and life rafts are crucial. These life-saving vessels must be readily accessible, and their deployment should be straightforward, even in challenging conditions. Engineering these systems requires considerations of weight, balance, and buoyancy to ensure they operate effectively in critical moments. Navigation systems are another pivotal safety component. Modern boats are equipped with sophisticated navigation technology, including GPS, radar, sonar, and electronic charting systems. The accuracy and reliability of these systems are paramount, as they enable precise navigation, avoidance of obstacles, and communication with other vessels. Furthermore, marine engineers work to ensure these systems are robust and can withstand the marine environment's corrosive forces. Communication systems are yet another aspect of boat safety that falls under the purview of engineering. These systems enable real-time communication with other vessels, coastal authorities, and emergency services. Safety depends on the ability to send and receive information, particularly in situations such as distress calls or search and rescue operations. Lastly, the structural integrity of a boat itself is a safety concern. Engineers must ensure that the materials used in the construction techniques employed meet rigorous safety standards. This involves stress analysis, material selection, and maintenance protocols to keep the vessel in seaworthy condition. Failure to meet these standards can result in catastrophic accidents and loss of life. In summary, the safety of boats is an engineering challenge that encompasses the design of life-saving equipment, navigation systems, and the structural integrity of the vessel. Engineers in the maritime industry must continually innovate and adapt to evolving safety standards and technology to protect passengers and crew during their journeys at sea. The quest for safety at sea remains a paramount concern, and it is a testament to the essential role that engineering plays in the maritime world. Boats represent marvelous feats of engineering that seamlessly blend principles of physics, mathematics, and intricate design to navigate the world's waterways. These vessels, ranging from small rowboats to massive ocean liners, have been instrumental throughout history, playing pivotal roles in exploration, trade, and recreation. A comprehensive understanding of the core principles governing their operation, buoyancy, propulsion, stability, and control enables us to develop a profound appreciation for the remarkable science that underpins their existence. The principle of buoyancy, as eloquently elucidated by Archimedes, is the cornerstone of a boat's ability to stay afloat. When a boat is immersed in water, it displaces an amount of water equal to its own weight, resulting in an upward buoyant force. This fundamental concept not only keeps boats afloat but also dictates the way they float and interact with water. Engineers meticulously design the shape and structure of the boat's hull to optimize this interaction, ensuring that the vessel remains buoyant while minimizing water resistance. Propulsion is another pivotal aspect of boat engineering. Boats can be powered by a range of methods, such as human effort through oars, harnessing the natural force of the wind with sails, or using various mechanisms, including engines, to create forward motion. These propulsion systems adhere to the immutable laws of physics, such as Newton's third law of motion, which dictates that every action has an equal and opposite reaction. The practical application of these principles results in the ability to propel boats through the water, whether it's through the rhythmic stroke of oars, the billowing of sails in the wind, or the roar of an engine. Stability in boat design is a paramount concern, and it involves the careful placement of weight, ballast, and the vessel's shape. Boats must strike a balance to prevent capsizing or excessive tilting, especially in rough waters. For sailboats, the inclusion of a keel, a substantial fin or bulb beneath the boat, serves as a counterbalance to the forces exerted by the wind in the sails. This engineering marvel ensures that even in adverse conditions, boats remain stable and can maintain their equilibrium. Control and navigation in the world of boating are complex yet elegant. Boats are equipped with rudders and other control mechanisms that use principles of fluid dynamics and hydrodynamics to alter the vessel's direction. The shape and positioning of the rudder play an instrumental role in determining how water flows around it, enabling precise steering and maneuverability. This meticulous engineering affords boaters the ability to chart their course and navigate through intricate waterways, opening up endless possibilities for exploration and travel. Safety is an overarching concern in boat engineering. The field encompasses designing life-saving equipment, such as life jackets and lifeboats, as well as implementing navigation systems, including GPS and radar, to ensure that passengers and crew can navigate with confidence. Engineers continually work to improve safety measures, reducing the risk of accidents and enhancing the overall boating experience. In sum, boats are not just vessels, they represent the harmonious convergence of science, technology, and design. Their rich history and modern ubiquity make them a source of fascination and admiration for people all over the world. Whether you're a seasoned sailor or someone who merely appreciates the sight of boats in a harbor, taking a moment to reflect on the intricate engineering that propels these vessels gracefully across the water is an invitation to marvel at the genius of human ingenuity. So, next time you set sail or gaze upon a boat, remember the complex physics, mathematics, and design that make these maritime marvels possible. Thank you.